In this lesson, EE301, we're going to be discussing AC series and parallel elements. However, our primary focus will be addressing a lot of the common mistakes we see in AC circuit analysis, including mistakes with the voltage divider and current divider rules. Alright, so starting off, one of the common mistakes we see is confusing the reactance for either a capacitor or inductor with the actual capacitance and inductance values of those components. So if we have a capacitor and we see anything attached to that capacitor in units of farads, we need to convert that to its reactance, and that should be in units of ohms. And we just use our 1 over omega c formula to get to reactance. Likewise with an inductor, if we see anything with the units of henries, we again need to convert that to reactance, and we do that by the formula omega times the inductance is equal to its reactance. Okay. Now, as a natural extension of that, a lot of times it's confusing whether to use omega or F when calculating its values. Now, to demonstrate that concept, we'll put in a time domain voltage source, and we'll put in our voltage peak value of 170, multiply that by a cosine of 1000t. Right, in this case, there's no 2 pi factor attached to that term, so this is omega. Whereas if we had the same source, but there was a 2 pi and then 1000 t, this 1000 would be F, units being hertz. Alright, so next, a lot of the time we confuse voltage RMS with voltage peak values, similarly current RMS and current peak values. Well, when you are solving these problems, you need to have them in RMS terms, which are attached to the phasors. And how you do that is you grab the peak values, right, this is a voltage peak, and voltage RMS is simply equal to voltage peak divided by root 2. Similarly, current RMS values are peak current by root 2. And you can just rearrange that to solve for your voltage peak if you need to go back to the time domain. Other than that, a lot of times we'll incorrectly convert rectangular to polar forms, and we'll lose track of our signs when adding up impedances. Especially important, right, for capacitors and inductors that have the negative J or the positive J respectively. And I'll add one more common mistake is when we're calculating these using our calculators, a lot of times we will not put the parentheses in the correct places, which will give us an incorrect answer. Moving on to mistakes applying the voltage divider rule, we see that we'll confuse, right, the E right here in our voltage divider rule as the voltage drop across the impedance in series. Since E is typically used as the symbol for the source, voltage source, and not necessarily the voltage across a series of elements, it's better to think of the formula in these terms, right? So if we're looking for a particular voltage source, we'll do the voltage drop right across these equivalent elements, and instead of Z total, we're going to say Z equivalent series. Right? Because when we think of Z total, we think of the entire circuit, which may not be a completely series circuit. So if we write in this way, we're less likely to make these types of mistakes. So if we're trying to find the voltage drop from node A to B, right? VA of AB would be this drop right here. We would set up first by finding our Z equivalent series equal to Z of R1 plus Z of C plus Z of R2. And these are all vector terms. And then VAB would be equal to VCN, right? That goes from here to here. The voltage drop between those two nodes multiplied by the impedance, the element of the impedance that we're looking for the particular voltage drop across, over the equivalent series impedance. Moving on to the current divider rule, a couple mistakes that we often see is I total. Again, I total. A lot of times we think of I total as the current that comes from a source. A better way to think of that would actually be, right, the current that feeds into our parallel element. So I'm going to label it I equivalent, parallel, and then we have Z equivalent over Z of X. And again, this lines up with what we have on the equation sheet. Additionally, if we have series elements, right, in one of our parallel branches, we need to first find the equivalent series impedance before we use our current divider rule formula. So, in this case, Z equivalent parallel is equal to Z of L in parallel with, right, this Z equivalent series. Right, and that's these three elements right here. So, to calculate I2, we would put the current flowing into that I equivalent for those two parallel elements. We would find the equivalent parallel, and then we would put Z equivalent series on the denominator, because we're interested in I2, which goes along this path with those three series impedances. So now we'll walk through a couple of practice problems. The first one we're going to do is going to require us to use the voltage divider rule. So that'll be this one right here. So my first steps are going to be to take a look at the circuit, and first I'm going to notice that my voltage source is in a phasor. So the voltage they give me is an RMS, which is good. And next I'm going to take a look at my inductor and capacitor, and I see that they're given in terms of ohms, so that these are their reactances. But I am going to need to add the positive J to my inductor and the negative J to my capacitor in order to get the impedances for both of these terms. Additionally, I'm going to go ahead and I'm going to add additional labels to these nodes, which will help me as I work the voltage divider rule. Alright, so first I need to find the total impedance for the circuit. And what I have is a 40 ohm resistor in series with two parallel paths. First one consists of a 50 ohm inductor, and that's in parallel with three elements in series: a 30 ohm resistor, a 60 ohm resistor, and a 10 ohm capacitor. Once I calculate all that, I'll get a CFT equal to 74.6 ohms with a phase angle of 32 degrees. Okay, so my next step will be to find IT using Ohm's law. Right, so I'll divide my voltage source by my total impedance, plugging in the values for both of those, and that will give me 3.22 amps, angle minus 32 degrees. Okay. So at this point, I know the current that is going through the 40 ohm resistor, but I don't know the distribution of currents through the two parallel paths, nor do I know the voltage drop from node A to node D, right? The voltage drop across those two parallel branches. So if I use Kirchhoff's voltage law and I find the voltage drop across this 40 ohm resistor, I can then find out the voltage drop from A to D. So just using Ohm's law, I can compute the voltage drop across that 40 ohm resistor. Which is 128.6 volts, phase angle minus 32 degrees. Okay, so now, again, Kirchhoff's voltage law. VA is equal to, VAD is equal to E minus voltage drop across that 40 ohm resistor. So 240 minus 128.6 minus 32 degrees, and I get 147.8 to 7.6 degree volts. Alright, so, like I said, that's the voltage drop from this point node A to node D. And also the voltage drop across these three series elements: the 30 ohm resistor, 60 ohm resistor, and the 10 ohm capacitor. So voltage drop of R is equal to VAD CR over Z equivalent series. So plug in the values. So 60 ohm resistor over the sum of those three series elements. And I find that voltage drop is 98 volts, phase angle 34 degrees. At this point, we'll do one more practice problem, incorporating the current divider rule, so we'll just focus in on part A of example 8, which requires us to find I2 using current divider rule. So that's right here. Okay. Again, just upon cursory inspection, I see that I'm getting a phasor, so I have my volt RMS already. For the inductors and capacitor, I'm given the reactances as I see that the ohms, but I just want to make sure I add in the appropriate J for each one of those to get the impedance values. So again, first step, again, will be very similar. I need to find my total impedance for the whole circuit. So I have that 20 ohm resistor plus 2 parallel paths, a 40 ohm inductor in parallel with 60 ohm resistor plus minus a 30 ohm capacitor, and these are in series with another 50 ohm inductor. Right, if I calculate all that, I'll get CT of 97.22 ohms, angle 62 degrees. So now IFT is found just using Ohm's law. My source divided by Z total is equal to 120 over that Z total value that we just computed. And my resultant current is 1.23 amps minus 62 degrees. Alright, so that's that value entering node A, which is then split between I1 and I2, which sets us up for our current divider. Alright, now I can solve for I2 using the current divider rule, which states that I need the total current going into that node, which in this case is I of t times my Z equivalent over my Z2. Alright, so in this case I need to first find Z equivalent. So that's 1 over J40 ohms plus 1 over 60 minus J30 ohms. All of that quantity to the negative first power. And my resultant value is 44.11 ohms, angle 53.97. So plug that in. I have to take again the sum of the 60 ohm resistor plus the minus J 30 ohms. And that gives me a final answer of 812 milliamps, angle of 19 degrees. That's all for today. If you have any additional questions, just refer them to your instructor.